In the early hours of June 13, 1944, just 1 week after the Allied forces stormed the beaches of Normandy, a strange and terrifying new sound pierced the night sky over southern England. It was a peculiar, pulsating roar, unlike anything heard before in the war. Those who witnessed it described a small, pilotless aircraft with a flame shooting from its tail, traveling at incredible speed across the darkness. When the engine suddenly cut out, there would be a few seconds of eerie silence, followed by a devastating explosion. The age of the robot bomb had arrived, and with it came one of the most urgent technical intelligence challenges of the entire war. The weapon was officially designated Fieseler Phi 103 by its German creators, but it would become infamous by another name, the Vergeltungswaffe 1, or Vengeance Weapon 1. To the British public and military, it was simply the V1, though it earned many other names during its reign of terror: the Doodlebug, the Buzz Bomb, and the Flying Bomb. This revolutionary weapon represented an entirely new form of warfare, the world's first operational cruise missile, and understanding how it worked became a matter of life and death for millions of people living in southeastern England. The story of how British engineers unlocked the secrets of the V1, particularly its sophisticated guidance system, centered around a precisely engineered gyroscope, is a remarkable tale of scientific detective work, courage, and ingenuity under the most extreme pressure imaginable. It involved bomb disposal experts risking their lives to retrieve intact components, brilliant engineers working around the clock to understand alien technology, and a desperate race to develop countermeasures before the weapons could turn the tide of the war. To understand the significance of what British engineers discovered, we must first understand the context in which the V1 was developed and the immense challenge it represented. By 1943, Nazi Germany found itself in an increasingly desperate strategic position. The Luftwaffe had failed to achieve air superiority over Britain, the Eastern Front was consuming enormous resources, and the German High Command knew that an Allied invasion of Western Europe was inevitable. Adolf Hitler became obsessed with the idea of Wunderwaffen, or wonder weapons, that could somehow reverse Germany's fortunes through technological superiority rather than conventional military strength. The V1 flying bomb emerged from this obsession, though its development actually predated the war's darker days. The concept originated with engineer Robert Lusser at the Fieseler Aircraft Company, working in collaboration with Fritz Goslau of the Argus Engine Company. Their goal was to create a simple, cheap, and effective unmanned aircraft that could deliver a substantial explosive payload to enemy targets without risking the life of a pilot or requiring the sophisticated navigation equipment of a conventional bomber. The design that emerged was, in many ways, brilliantly simple. The V1 was essentially a small aircraft with a cylindrical fuselage measuring just over 25 feet long, stubby wings spanning about 17 feet, and a distinctive pulse jet engine mounted on top of the fuselage. The weapon weighed approximately 4,800 pounds at launch, with a warhead containing roughly 1,800 pounds of Amatol-High explosive. It was designed to be launched from a long catapult ramp using a chemical reaction rocket motor, though later versions could be air-launched from modified Heinkel bombers. What made the V1 truly revolutionary, however, was not its airframe or engine, but its guidance system. The Germans had managed to create a relatively reliable autopilot that could guide the weapon across the English Channel to its target with no human intervention whatsoever. For 1944, this was extraordinary technology. The heart of this guidance system was a sophisticated three-axis gyroscope, a masterpiece of precision engineering that represented some of the finest mechanical design work of the entire war period. When the first V1s began falling on England in June 1944, British intelligence had already been aware of the weapon's existence for some time. Reconnaissance. Photographs of Peenemünde and other German test facilities had shown unusual ramp structures and intelligence reports from resistance networks across occupied Europe had provided fragmentary information about a new secret weapon. The British codenamed the project Crossbow and had even launched bombing raids against suspected V-weapon facilities. However, knowing about the weapon's existence and understanding how it actually worked were two very different things. The initial attacks were concentrated on London and the surrounding areas. The V-1s were launched from sites in northern France, primarily in the Pas-de-Calais region, taking advantage of the relatively short distance across the Channel. The weapons flew at approximately 400 miles per hour at altitudes between 2,000 and 3,000 feet, making them difficult but not impossible to intercept with the fighter aircraft and anti-aircraft guns available at the time. For the British military and civilian authorities, the V-1 represented a unique and urgent threat. Unlike conventional bombing raids, which could be predicted, intercepted, and defended against using established procedures, the V-1s came at all hours, with no warning, and in numbers that threatened to overwhelm the defenses. Moreover, the psychological impact of a pilotless weapon was profound. There was something particularly unsettling about a machine, devoid of any human presence, methodically seeking out civilian targets. The British response to the V-1 threat operated on multiple levels simultaneously. Fighter Command redeployed squadrons to intercept the weapons. Anti-aircraft batteries were moved to the southern coast to create a gun belt through which the V-1s had to pass. Barrage balloons were raised over likely target areas. But all of these defensive measures required one critical element, a detailed understanding of how the weapon actually worked, and that meant obtaining intact examples for examination. This is where the story becomes particularly remarkable, for it involved some of the bravest and most skilled individuals in the entire British military, the bomb disposal teams of the Royal Engineers. These men, many of them volunteers, faced a task of almost unimaginable danger. When a V-1 crashed without exploding, which happened with surprising frequency due to various malfunctions, someone had to approach it, assess whether it could be safely examined, and, if possible, recover its components for technical intelligence purposes. The problem was that the V-1 was equipped with multiple fusing systems specifically designed to prevent exactly this kind of examination. The Germans knew that the British would attempt to recover crashed weapons, and they had incorporated numerous anti-handling devices into the design. Some V-1s had impact fuses that would detonate on contact with the ground. Others had time delay fuses that would trigger the warhead minutes or even hours after landing. Still others had electrical systems that would trigger detonation if disturbed. And in many cases, the crash itself would damage these fusing systems in unpredictable ways, making even a weapon that should be relatively safe potentially deadly. The men who approached these crashed V-1s did so knowing that their next step might be their last. They worked slowly and methodically, often in the immediate aftermath of an attack, when emotions were running high and the pressure to obtain intelligence was intense. They carefully examined the exterior of the weapon, looking for signs of damage or booby traps. They gently probed connection points and access panels, and when they believed it was safe, they began the delicate process of disarming the fuses and removing components. One of the most significant early recoveries occurred in late June 1944, just weeks after the first attacks. A V-1 had crashed in relatively soft ground in Kent, and although its warhead had been damaged, much of its guidance system remained intact. The bomb disposal team that recovered it carefully extracted several key components, including, most crucially, the gyroscope assembly and the control servos that connected it to the flight controls. These components were immediately transported under guard to the Royal Aircraft Establishment at Farnborough, the primary center for British aviation research and development. There, a team of engineers and scientists that had been hastily assembled for the purpose of understanding the V-1 threat began their examination. What they discovered would prove crucial not only for developing immediate countermeasures, but also for advancing the entire field of guided missile technology. The gyroscope they examined was unlike anything they had seen before in an operational weapon system. It was a 3-axis unit, meaning it could sense rotation in all 3 dimensions of space: pitch, roll, and yaw. This was necessary because the V-1, unlike a conventional aircraft, had no pilot to correct for deviations from its intended course. The gyroscope had to provide a stable reference point against which any unwanted rotation could be measured and corrected. What impressed the British engineers most was the precision of the manufacturing. The gyroscope rotor had to spin at very high speeds, something on the order of 10,000 revolutions per minute, while maintaining almost perfect balance. Any imbalance would cause precession, a phenomenon where a spinning gyroscope drifts away from its intended orientation. The bearings had to be manufactured to tolerances measured in microns, and the entire assembly had to be hermetically sealed to prevent contamination from dust, moisture, or the extreme vibrations generated by the pulse jet engine. The Germans had achieved this using some remarkably clever engineering solutions. The gyroscope housing was machined from solid aluminum alloy, providing both strength and lightweight. The rotor itself was carefully balanced and mounted on jeweled bearings, similar to those used in high-precision watches. The entire unit was suspended in a gimbal system that allowed it to maintain its orientation regardless of the movement of the V-1 around it. And critically, it had included electrical pickups that could sense any deviation from the desired orientation and send correction signals to the servo mechanisms that controlled the V-1's flight surfaces. But the gyroscope, remarkable as it was only one part of the guidance system. The British engineers also discovered a sophisticated magnetic compass that provided directional reference, ensuring the V-1 flew on the correct heading toward its target. This compass had to work despite the enormous magnetic interference generated by the pulse jet engine and the electrical systems. The Germans had solved this problem by careful shielding and by positioning the compass as far from sources of interference as possible. Perhaps most ingeniously, the British discovered how the Germans had solved the problem of determining when the V-1 had traveled far enough to reach its target. The solution was elegantly simple. A small propeller mounted in the nose of the weapon was connected to a mechanical counter. As the V-1 flew through the air, the propeller would spin, and with each revolution, it would advance the counter by a small increment. The counter was preset before launch based on the distance to the target. When it reached 0, it would trigger the dive control, pushing the V-1's elevators down and causing the weapon to enter a steep dive toward the ground. This distance measuring system worked surprisingly well, despite its mechanical simplicity. The Germans had carefully calibrated the propeller so that a specific number of revolutions corresponded to a specific distance traveled. Of course, this system had inherent inaccuracies. If the V-1 encountered headwinds, it would travel less distance per revolution. If it had tailwinds, it would travel more. The altitude at which it flew also affected air density, and thus the propeller's rotation rate. These factors meant that V-1s aimed at a specific target would actually impact over a considerable area, sometimes miles from the intended point. But for a terror weapon aimed at a large city, this level of accuracy was sufficient. The British engineers documented every aspect of what they found with meticulous care. Technical drawings were produced showing every component in detail. The gyroscope was disassembled step by step, with photographs taken at each stage. Samples of materials were sent for metallurgical analysis to understand exactly what alloys the Germans were using. The electrical circuits were traced and documented. Every screw, spring, and wire was catalogued. This detailed understanding of the V-1's internal workings immediately began to pay dividends. The engineers could now predict with much greater confidence how the weapon would behave under different conditions. They understood its vulnerabilities as well as its strengths. And most importantly, they could begin to develop specific countermeasures designed to exploit those vulnerabilities. One immediate application was in refining the defensive tactics used by fighter aircraft. Pilots had initially found the V-1s challenging to intercept. At 400 miles per hour, the weapons were faster than many British fighters at low altitude. Catching up to one required a sustained full-power dive, and once alongside, pilots had discovered that shooting down a V-1 was more difficult than it appeared. The weapons were small, tough, and packed with explosives. Getting too close when firing risked being caught in the explosion when the warhead detonated. Armed with detailed knowledge of the V-1 structure, Royal Air Force tactics specialists could advise pilots on the most effective way to destroy the weapons. They learned that the pulse jet engine, while robust, was vulnerable to damage from even small caliber fire. The fuel lines running along the fuselage could be ruptured. The control surfaces, relatively lightly built, could be damaged by cannon fire. Some particularly skilled pilots even developed the technique of flying alongside a V-1 and using their own wing to disturb the airflow over the weapon's wing, causing it to roll and crash without firing a shot. The intelligence gathered from the recovered gyroscope and other components also proved crucial in understanding the limitations of the V-1's guidance system. The engineers realized that the gyroscope-based autopilot, while sophisticated, was still purely mechanical system subject to drift and error accumulation. Over the course of a flight across the channel, small errors in the gyroscope's indication would compound, causing the V-1 to gradually deviate from its intended course. This meant that V-1s aimed at central London might actually impact anywhere in a broad area around the city. This understanding led to one of the more controversial defensive measures implemented by the British: the deliberate dissemination of false information about where V-1s were landing. Through double agents controlled by British intelligence, the Germans were fed reports suggesting that V-1s were overshooting their targets and landing well north of London. In reality, most were falling short or hitting the southern outskirts of the city. The Germans, believing these false reports, adjusted their aim, causing subsequent V-1s to fall even shorter, increasingly in less densely populated areas south of the Thames. This deception, while ethically questionable, as it meant deliberately allowing some areas to remain at risk while protecting others, undoubtedly saved many lives in central London. The examination of the V-1's gyroscope also revealed something that British intelligence found deeply concerning. The Germans clearly had significant expertise in precision mechanical engineering and inertial guidance systems. This suggested that even more sophisticated weapons might be in development. And indeed, intelligence reports were already indicating that a second vengeance weapon, the V-2 rocket, was being prepared. If the Germans could produce gyroscopes of this quality for a relatively simple cruise missile, what might they be capable of in a ballistic missile traveling at supersonic speeds? This concern led to an intensified effort to understand German manufacturing capabilities. Intelligence officers interrogated German prisoners, particularly those with technical backgrounds, about the production of precision instruments. They analyzed captured documents for any reference to gyroscope manufacture. They studied reconnaissance photographs of German factories looking for facilities that might be producing these components. What they discovered was that Germany had a long-standing tradition of precision engineering, particularly in optical and mechanical instruments, and that this expertise had been systematically harnessed for military purposes. The recovered V-1 components found their way to multiple British research facilities. In addition to Farnborough, examples were sent to the Telecommunications Research Establishment, which was interested in the electronic aspects of the guidance system, and to the Armaments Research Department, which wanted to understand the fusing mechanisms. Each facility brought its own expertise to bear, and the pooled knowledge proved invaluable. One particularly interesting discovery involved the V-1's air pressure-based altitude control system. The engineers found that the weapon used a simple aneroid barometer, similar to those used in aircraft altimeters, to maintain its cruising altitude. This barometer was connected to the elevator controls through a servo mechanism. If the V-1 climbed above its preset altitude, the changing air pressure would trigger a correction that lowered the nose. If it descended too low, the opposite correction would be applied. The elegance of this system impressed the British engineers. It was entirely self-contained, requiring no external reference or input. It was also relatively immune to countermeasures. Unlike radio guidance systems, which could potentially be jammed or deceived, a mechanical barometer simply responded to physical reality. However, the engineers did note one potential vulnerability. The system assumed a standard atmosphere. In unusual weather conditions, particularly with abnormal pressure systems, the altitude control might not work as intended. This observation led to some creative thinking about potential countermeasures. Could weather forecasting be used to predict when atmospheric conditions might cause V-1s to fly higher or lower than intended? Could this information be used to optimize the positioning of anti-aircraft guns? While these ideas were explored, they ultimately proved impractical, given the short warning time between a V-1 being launched and arriving over England. As more and more V-1 components were recovered and examined, the British engineers began to build up a comprehensive understanding not just of individual systems, but of how they all work together as an integrated whole. They mapped out the electrical circuits that powered the gyroscope and servo mechanisms. They understood how the magnetic compass provided directional input. They traced how the distance-measuring propeller ultimately triggered the final dive, and they saw how the barometric altitude control kept the weapon at a consistent height throughout its flight. This systems-level understanding was perhaps even more valuable than the details of individual components. It allowed the British to predict how the V-1 would respond to various scenarios. What would happen if one control surface was damaged? How would the guidance system react to sudden changes in wind speed or direction? Could the weapon recover from severe turbulence or the shock wave from an anti-aircraft burst? The answers to these questions informed everything from fighter tactics to gun deployment. They also provided the basis for testing potential countermeasures. If you knew exactly how the guidance system worked, you could design interference methods specifically tailored to defeat it. While the V-1's mechanical systems were largely immune to electronic jamming, understanding their operation suggested other approaches. One concept that was explored, though never implemented, was the idea of using powerful searchlights to illuminate V-1s at night. The theory was that the sudden, intense light might affect the gyroscope if any part of its operation was optically based. Testing of the recovered gyroscope confirmed that this wouldn't work, as the system was entirely mechanical and sealed. But the fact that such ideas were being considered shows how thoroughly the engineers understood the weapon and how creative they were in thinking about ways to defeat it. The intelligence gathered from the V-1 examination also contributed to broader strategic decisions. The British bombing campaign against V-1 launch sites in France was guided in part by understanding which facilities were most critical to the weapon's operation. If the gyroscopes were particularly difficult to manufacture, then factories producing them became priority targets. If the launching catapults required specific construction materials, then supply routes for those materials were interdicted. By late summer of 1944, the immediate threat from the V-1 was beginning to diminish. Not because the weapons had stopped coming, they continued to be launched in large numbers until the Allied advance overran the launch sites in northern France, but because the defenses had become much more effective. Fighter pilots, armed with better tactics and faster aircraft, were destroying an increasing percentage of the incoming weapons. The anti-aircraft guns, now positioned in a coordinated belt along the coast and equipped with proximity-fused shells, were achieving remarkable success rates, and the barrage balloons over London were catching their share as well. The effectiveness of these defenses owed much to the detailed understanding of the V-1 that had been gained through the examination of recovered components, particularly the gyroscope. By understanding exactly how the weapon flew, how it maintained its course and altitude, and what its limitations were, British defenses could be optimized to exploit those limitations. It was a perfect example of how technical intelligence could translate directly into saved lives. But the story of the V-1 gyroscope examination had implications that extended far beyond the immediate war situation. The British engineers were not just looking at these components as enemy weapons to be defeated. They were also seeing them as examples of advanced technology that could potentially be adapted for British use. The precision manufacturing techniques, the gyroscope design, the servo mechanism integration, all of these represented knowledge that could be applied to British missile development programs. After the war, when British engineers began developing their own guided missiles, they drew heavily on what they had learned from the V-1. Not that they simply copied the German design, technology had moved on, and there were better approaches available. But the fundamental principles of inertial guidance, the importance of precision manufacturing, the challenges of integrating multiple systems in a harsh vibration environment, these lessons learned from examining the V-1's gyroscope proved invaluable. The individuals who had worked on examining the V-1 components became some of Britain's leading experts in guided missile technology. Their wartime experience gave them a unique perspective and a deep understanding of both the practical and theoretical aspects of missile guidance. Many went on to play crucial roles in Britain's post-war defense industry, contributing to the development of weapons systems that, ironically, owed much to what they had learned from their wartime enemy. It's worth reflecting on the human element of this story. The bomb disposal officers who risked their lives to recover intact V-1 components rarely received public recognition for their work. It was classified, dangerous, and often thankless. Yet, without their courage, none of the technical intelligence that followed would have been possible. They were ordinary soldiers, many of them not much more than boys, performing extraordinary acts of bravery day after day. The engineers at Farnborough and other research facilities worked under immense pressure. They knew that every hour they spent examining the V-1 components was an hour during which more weapons might be falling on British cities. They worked around the clock, surviving on tea and cigarettes, driven by the knowledge that their work mattered, that the insights they gained could save lives. Many of them had families living in London, in the very areas being targeted by the weapons they were studying. The work was not abstract or theoretical to them, it was deeply personal. And there were the scientists and mathematicians who took the raw technical data and turned it into actionable intelligence. They calculated trajectory predictions, analyzed error patterns, developed mathematical models of the guidance system behavior. Their work, conducted with slide rules and mechanical calculators, forms that seem primitive by modern standards, was nonetheless extraordinarily sophisticated. They were pioneers in what would later become the field of systems analysis, using rigorous mathematical methods to understand complex technological systems. The examination of the V-1's gyroscope also provides an interesting case study in technological convergence. The Germans had developed their guidance system independently, drawing on their own engineering traditions and expertise. The British, working from different starting points and with different design philosophies, had been developing their own guided weapon systems. Yet, when British engineers examined the German gyroscope, they found solutions to problems that were often remarkably similar to those they had developed independently. This convergence suggests that for certain technical challenges, there may be optimal solutions that different engineers working independently will tend to discover. The need to create a stable reference frame in a vibrating, accelerating missile inevitably leads to the use of gyroscopes. The need for precision at high rotation speeds inevitably leads to carefully balanced rotors and low-friction bearings. The need for electrical outputs inevitably leads to pick-off systems of various kinds. The specific implementations might differ, but the fundamental approaches converge. Yet there were also distinctly different design philosophies evident in the V1 compared to British weapons of the period. The Germans had prioritized simplicity and ease of manufacture. The V1 was designed to be produced in large numbers by semi-skilled workers in dispersed factories. It used relatively simple materials and construction techniques. This was partially a matter of necessity, given Germany's resource constraints and the vulnerability of its factories to bombing. But it was also a reflection of the weapon's intended role as a terror weapon where accuracy was less important than quantity. British missile designs of the same era tended to be more sophisticated, but also more complex and expensive to manufacture. They aimed for higher accuracy and reliability, but at the cost of production speed and numbers. This reflected different strategic priorities and different resource availabilities. Neither approach was inherently superior, they were simply optimized for different objectives. The V1 campaign continued until March 1945, when the last launch sites were finally overrun by Allied forces. By that time, over 9,000 V1s had been launched against England, with roughly 7,500 reaching the British defensive zone. Of these, about 4,000 made it through the defenses to impact on British soil. These weapons caused tremendous damage and loss of life. Over 6,000 civilians perished, and many more were injured or left homeless. Yet the toll could have been far worse. Estimates suggest that without the effective defenses that had been developed, casualties might have been several times higher. And those defenses, particularly the refined fighter and gun tactics, owed much to the detailed understanding of the V1 gained through technical intelligence, particularly the examination of the guidance system centered on that precisely engineered gyroscope. The story of British engineers examining the V1 gyroscope is ultimately a story about the nature of technological warfare in the modern age. It illustrates how quickly new technologies can emerge and how they can fundamentally change the character of conflict. It shows the importance of technical intelligence and the bravery of those who gather it. It demonstrates how scientific understanding can be rapidly translated into practical defensive measures. And it highlights the complex interplay between engineering, tactics, strategy, and intelligence that characterizes modern warfare. For the engineers who first carefully disassembled that recovered gyroscope in the summer of 1944, there must have been a mixture of emotions. Admiration for the German engineering skill evident in every component. Urgency driven by the knowledge that this weapon was threatening their homeland. Curiosity about how each system worked and how it might be countered. And perhaps also a recognition that they were witnessing the future of warfare, where pilotless weapons guided by sophisticated mechanisms would play an increasingly important role. They could not have known as they peered at that spinning rotor and traced those electrical connections that they were helping to lay the groundwork for an entire industry that would emerge in the decades to come. The cruise missiles that would become standard weapons in the arsenals of nations around the world. The space programs that would use inertial guidance systems to navigate to the moon and beyond. The autonomous vehicles that would one day navigate our streets. All of these would build on the fundamental principles that those wartime engineers were documenting and understanding. The gyroscope they examined was a product of its time, built with the materials and manufacturing techniques available in the 1940s. Modern gyroscopes using laser ring technology or microelectromechanical systems are vastly superior in every measurable way. Yet the fundamental principle remains the same. A rotating mass maintains its orientation in space and can serve as a reference for navigation and guidance. The V1's gyroscope was, in its own way, a masterpiece of its era, and the British engineers who unraveled its secrets played a crucial role not just in defending their country, but in advancing human technological knowledge. As the war in Europe drew to its close and the V-1 threat receded into history, the lessons learned from examining these weapons were carefully documented and preserved. The gyroscopes and other components recovered from crashed V-1s were kept for study and training purposes. The reports written by the engineers at Farnborough and other facilities were classified but carefully archived, and the knowledge gained was quietly incorporated into Britain's own developing missile programs. In the immediate post-war years, as the Cold War began to take shape, this knowledge became even more valuable. The world was entering an era where guided missiles would be crucial strategic weapons. The nations that understood how to build and defend against such weapons would have significant military advantages. Britain, thanks in part to the detailed examination of German V-weapons during the war, entered this new era with a substantial head start in understanding missile guidance technology. The captured V-1 components also provided training opportunities for a new generation of engineers and scientists. Young technicians who had not been involved in the wartime examination could study the actual hardware, take apart the gyroscopes, examine the servo mechanisms, and learn from real examples rather than just theoretical descriptions. This hands-on education proved invaluable in developing Britain's indigenous missile capabilities. What the British engineers discovered when they examined that V-1 gyroscope was more than just the details of one weapon system. They discovered insights into German engineering philosophy, manufacturing capabilities, and technical priorities. They learned about the state of precision manufacturing in wartime Germany. They understood the trade-offs the German designers had made between accuracy, reliability, cost, and production speed. And they gained a deeper appreciation for what was possible with the technology of the era. This knowledge had intelligence value that extended beyond the immediate tactical situation. Understanding Germany's capabilities in precision manufacturing helped Allied intelligence assess what other weapons might be in development. If Germany could produce gyroscopes of this quality, what else might they be capable of? This question drove further intelligence-gathering efforts and helped inform Allied strategy in the final year of the war. The V-1 gyroscope examination also contributed to the broader Allied effort to understand and potentially exploit German scientific and technical achievements. As the war ended, Allied teams fanned out across Germany seeking not just weapons, but also the scientists, engineers, and technicians who had created them. The knowledge gained from examining the V-1 and other weapons helped these teams understand what to look for and which German experts might be most valuable. Looking back from our vantage point more than 80 years later, it's striking how much the examination of that V-1 gyroscope encapsulates about the nature of the Second World War. It was a conflict driven by industrial might and technological innovation. It was a war where scientific understanding could translate directly into military advantage, and it was a struggle where the ingenuity and courage of individuals, whether bomb disposal officers recovering components under fire or engineers working through the night to understand them, could make a profound difference in the outcome. The V-1 flying bomb was Germany's attempt to use technology to compensate for declining conventional military strength. It failed in its ultimate objective of forcing Britain out of the war or significantly disrupting the Allied invasion of Europe. But it succeeded in demonstrating the potential of guided weapons and in spurring a leap forward in defensive technology and tactics. The cat-and-mouse game between the V-1 and its defenses, played out in the skies over England in the summer and fall of 1944, was a preview of the technological arms races that would characterize the Cold War and continue to this day. The British engineers who examined that gyroscope were, in their own way, pioneers. They were among the first to systematically reverse engineer an enemy's advanced weapon system under wartime conditions. They developed methodologies for technical intelligence analysis that would be used and refined in conflicts for decades to come. And they demonstrated the vital importance of understanding not just what an enemy weapon does, but how it does it, because that understanding opens up possibilities for countermeasures that would otherwise remain hidden. Their work reminds us that modern warfare is as much about knowledge and understanding as it is about firepower and numbers. A single intact gyroscope, properly examined and understood, could contribute more to the war effort than a dozen destroyed V-1s whose secrets died with them in their explosions. This principle remains true today, where technical intelligence continues to play a crucial role in defense planning and strategy. The story of the V-1 gyroscope examination is also a reminder of the human cost of technological warfare. Every technical innovation, every weapon system, ultimately exists to harm human beings. The same engineering brilliance that created the V-1's sophisticated guidance system was directed toward the indiscriminate destruction of civilian areas. The same precision manufacturing that produced those beautiful gyroscopes was part of a larger effort to rain death from the skies on London and other cities. Yet the examination of the gyroscope also represents humanity at its best. The courage to face danger in the service of protecting others, the intellectual curiosity to understand complex systems, the ingenuity to turn knowledge into practical defensive measures. The individuals involved in this effort, from the bomb disposal teams to the engineers to the intelligence analysts, were using their skills and risking their lives to save others. Their story deserves to be remembered and honored. As we conclude this account, it's worth considering what became of those examined V-1 components. Some remained in Britain, carefully preserved as historical artifacts and teaching tools. Others made their way to the United States as part of intelligence sharing between the Allies. A few may have been destroyed in testing as engineers experimented with potential countermeasures. But the knowledge gained from examining them, particularly from that detailed study of the gyroscope and guidance system, that knowledge lived on and continued to shape the development of missile technology for decades. The V-1 flying bomb and its descendants transformed warfare. From being a curiosity, a desperate German gamble with a new type of weapon, guided missiles became one of the dominant weapon systems of the modern era. Today, cruise missiles, far more sophisticated than the V-1 but based on similar principles, are standard equipment in the arsenals of major military powers. The journey from that first examination of a recovered V-1 gyroscope to today's precision-guided weapons is a direct line of technological evolution. In remembering this story, we honor not just the technical achievement of understanding a complex weapon system under pressure, but also the broader struggle of which it was a part. The men and women who worked to understand and defeat the V-1 were engaged in a desperate fight against tyranny. Their work, whether defusing unexploded bombs, examining captured components, or developing defensive tactics, was all part of the larger effort to preserve freedom and defeat fascism. The gyroscope at the heart of the V-1's guidance system was, in the end, just a piece of precision machined metal, carefully balanced and mounted in gimbals. But what it represented, and what British engineers learned from examining it, transcended its physical form. It represented a challenge met, a threat understood and countered, and a step forward in humanity's complex relationship with technology. The story of its examination is a small but significant chapter in the larger history of the Second World War, and a reminder of how technical knowledge properly applied can help determine the outcome of great conflicts.